In this video, we are going to be taking a look at something called calorimetry. Calorimetry is a laboratory method of measuring the enthalpy of a reaction. So this activity goes along with the organizer that is on page 805. So if you want to get that out, really what I'm going to do is just highlight the stuff that's already there. Mostly what we wanted to do in that organizer is give you solid examples that you have as references. So I just want to go through and hit some of the highlights for you as far as that goes. And so the one thing that you always want to remember is that when we're doing calorimetry, you can't measure the temperature change of the system. You can only measure the temperature change of the surroundings. And so we need to assume that those two things are going to be 100%. Problem with that is we only are going to be able to measure the temperature change of the water that's involved. Whether the chemical is dissolved in the water or the material is in the water or the water's above the material or whatever, we need to assume that only the water is absorbing the energy or releasing the energy to the system. That's a dangerous assumption because you've got the container, you've got the air, and so forth. So when we do calorimetry in class, it is never 100% efficient in terms of transferring energy. But we make that assumption. All right, so for us, the system is going to represent, is going to be whatever the chemical is that we're interested in or the material that we're interested in. The surroundings is always going to be water. So since the surroundings is always going to be water, and water is not going to be boiling or freezing or anything like that, all we're going to be doing is changing the temperature of liquid water, the side with the surroundings is MC delta T. How much water did you use, what was its temp change, and multiply that by the specific heat of 4.184 joules per gram degree Celsius. For the system, however, it's going to depend upon what we're doing. Changes could be physical or they could be chemical. Regardless of that, we're going to go back and use this equation all the time, but the Q of the system is going to be a little bit different. So, I've got a couple of examples down here. If we're simply changing the temperature of a material, like a piece of metal, you're going to see an example further on down the page with that. Since you're only doing a temp change, once again, you're at MC delta T. Okay? However, if we're doing a state change, like melting or freezing or something like that, you're going to use M delta H because that doesn't have a temperature change. So the delta T falls away because a state change happens at a temperature plateau. If you're doing some sort of higher, more complicated activity, like dissolving an ionic substance in water, you're still doing M delta H. We're still breaking IMFAs. Remember that the delta H is involved when you are breaking bonds. The C is involved when you're simply changing motion. So if an ionic salt is going to dissolve in water, we're breaking those ionic bonds. So again, we're back to delta H. If we're burning something, we're doing delta H of the reaction or delta H of combustion in this case. If I am reacting an acid with a base, I can call it the delta H of neutralization. So that delta H subscript is going to be dependent upon what the phase change or the chemical processes that you're doing. But it's all the same. Notice that the Q of the system, if you are involving bonds at all, is going to be M delta H. So with that in mind, let's take a look at some examples. Okay, so to do something like this, we perform a reaction, we collect some enthalpy data. In order to do so, what are we doing? We're collecting the temperature change of the surroundings, the temperature change of the water. And we can measure that temp change, obviously, with a thermometer and see how much the energy is changing by. Okay, the assumption now is that whatever happened to the surroundings is going to be equal but opposite happening to the system. So that's idea number 2. Idea number 3, we're going to use that information to calculate the delta H and then give it an appropriate sign based upon our observations of temperature change. So these are the steps that are involved in all of the examples that we're going to go through today. All right, so the first example is the one I alluded to a little bit earlier. What if we just put a hot piece of metal into a cold piece of water? I can use that to figure out the specific heat in this way. So here's my information. I'm taking 33.95 grams sample of a metal. It's at 100 degrees because I have it sitting in boiling water. I'm going to take that metal and I'm going to transfer it to 100 grams of cold water. It's 16 degrees. And I'm going to allow that temperature to equilibrate. So the temperature of the metal is going to drop. The temperature of the water is going to rise until they get to the same temperature. And in this case, that temperature happens to be 21 degrees. So anytime all you're doing is changing the temperature of something, you are using MC delta T of surroundings equals MC delta T of system. So what we want to know is what's the specific heat of the system. So let me move the camera just a little bit more so you might be able to see it. I feel like this is coming in a little blurry, but hopefully you guys can see it okay. All right, so MC delta T equals MC delta T. Denominator is going to be the metal. The numerator is going to be the water. So I have 100 grams of water at this specific heat. It started out at 16, changed to 21. So what's my delta T? Notice that the delta T's are always going to be positive temp changes. That's just the easiest thing for you to remember. Always make the delta T absolute. In order to determine the sign, we'll worry about it a little bit later. Okay, and then for the system, we've got the mass of the metal, which was 33.95 grams, along with the delta T of the metal, started at 100 and dropped down to 21. Okay, so if I solve that problem, I get the specific heat of the metal is 0.780 joules per gram degree Celsius. So I can go on and use that number to help identify the metal if I need to. Hint, hint, there's an activity that you're going to do in the not too distant future that does that. All right, so here's an example of where we're not doing anything chemical in terms of bonding. All we're doing is changing the temp. Okay, on the back side of your organizer, there's several examples of where we are doing some bond changes. Okay, so here's the first one. What if I have 5 grams of silver nitrate and I dissolve it in 100 grams of water? And the temperature rises from 21.5 to 82.8. What's the heat of reaction for that material? Okay, so in order to solve that problem, I've got to remember that my surroundings is going to be MC delta T, but now my system is going to be M delta H, because now in order to dissolve the silver nitrate, I have to break ionic bonds. I have to dissociate those silver ions and those nitrate ions in water. Okay, so let's take a look. I've got MC delta T for the surroundings divided by M delta H. I'm going to do something here that is going to make you a little bit confused. When you have the chemical actually dissolved in the water, and this is something you want to put an asterisk next to, a note next to, something to remember. Anytime the chemical is in water, the mass is not just the mass of the water, the mass is the mass of the whole solution. So notice that I have 100 grams of water plus the 5 grams of silver nitrate. So that total mass of the solution is what I have to use. I only do that when the chemical has actually been dissolved in water. If the chemical is not dissolved in water, all I'm going to do is the mass of the H2O. But whenever the chemical is dissolved in water, I'm going to add those two together. Specific heat, temperature change, divided by the mass of the system, which was just the 5 grams of silver nitrate, I get 5,386.06 joules per gram. Okay, so that's my delta H in joules per gram. If I want it in kilojoules per gram, which is typically what we need to have in order to put it into a thermal equation, I'm going to take my joules per gram, multiply it by my molar mass, and then obviously convert to joules. So I wind up with a delta H that is 915 kilojoules per mole. I got one last step to do. I got to figure out what sign to give it. Is this an exothermic or an endothermic process? So what am I going to do to figure that out? I'm going to go back and I'm going to look and I'm going to see, all right, my water started out at 21.5, but it rose to 82.8. The temperature of the water, the temperature of the surroundings went up. Okay? That means the energy was being given off by the system, by the silver nitrate. As a result, what's my exothermic reaction? or what's my reaction? It's going to wind up being exothermic because the system gave off energy. So the sign that I need to give my delta H is actually a negative. Okay, so this one example, like I said, is going to be the one that may catch you the easiest, because you've got to remember that the mass is the mass of the solution, not just the mass of the water. Okay, and again, the other note that you want to take note of is look and see what happens to the temperature of the water. Since the temperature of the water rose, the surroundings was gaining energy, which means the system must be losing energy. So the system underwent an exothermic process. I'm going to give a negative sign for the delta H. All right, second example here. I've got a chemical reaction that takes place using 8.94 grams of the substance. The substance causes 75.82 grams of water to cool from a temperature of 22.4 to 14.3. What's the enthalpy of reaction in joules per gram? Well, in this case, again, the reaction is taking place in the water. So note what I need to do. I need to use the entire mass of the solution. Temp change of the solution is 22 down to 14.3. Mass of just the system was 8.9, so I get 321 joules per gram. But the question says, what's the enthalpy? I need to worry about the delta H. So the last thing I want to do is think, okay, what happened to the temp change? Well, it says the water cooled. The water is the surroundings. So if the water lost energy, where did that energy go? The energy must have gone into the system, into the chemical. So I'm going to put a positive 321 joules per gram for my answer. Okay, so you got to think what happened to my water. The opposite is happening to the chemical. And that's how you're going to figure out the sign. Okay, last example, now I have chemical is separate from the water. Okay, so there's two examples of where we had the chemical in the water. Here's an example where the chemical is not in the water, and we're actually going to do something like this a little ways down the road as well. So we've got a candle with a mass of 28.43 grams set up in a chimney calorimeter. You're going to see what a chimney calorimeter is later on. The calorimeter contains 125.08 grams of water at 18.9 degrees Celsius. Candle is lit and allowed to burn for 10 minutes. Okay, so really what's going on is the candle is underneath the water in the calorimeter. So the candle is separate. So I don't have a solution of water and candle. I have them separate. After 10 minutes, we blow out the candle. The temperature of the water is found to reach a peak of 37.2 degrees Celsius. After the candle cools, its mass is taken. The mass of unburned candle is 25.07. Calculate the heat of reaction in joules per gram of the candle wax. All right, so what are we going to do? I'm using MC delta T equals M delta H again because I'm breaking bonds, but I'm doing a whole chemical reaction. However, all I need to do, notice, all I need to do is use the mass of the water because the wax is not in the water. I guess I don't have that white paper anymore. The wax is not in the water. Temperature changes here. The amount of wax that actually burned, how much wax actually generated the heat that we're measuring, well, it's going to be the difference between those two. So keep that in mind. If your entire system didn't get used, in the calculation, you have to use whatever quantity actually did get used. So I do all this math, I get 2,850 joules per gram of wax, and I'm going to give it a negative. Do you know why I'm going to give it a negative sign? Think for a minute. So if you look, I started out with 18.9 degrees, wound up at 37.2 degrees in my water. So the water gained energy, which means the system must have lost energy. So the system underwent an exothermic process. Therefore, I give my delta H a negative. Okay, so these are the different kinds of calorimetry questions that you're going to come across in the unit. Hopefully, you've got good notes from having this conversation. You jotted some things down. If not, watch the video again, jot some things down. Moving forward, in the next couple activities, got some problem sets to do to practice. You've got a bunch of activities to do in the lab. Some of them you're just watching Me collect data. Some of them you are collecting data yourself, and I think with these I'm doing all the data collection. So anyway, there'll be videos accompanying the labs that we're going to do, and then you guys will work up the analysis. Okay, have fun.